add one signal here and then you can extrapolate to get like any rendering you see on the screen these days. Not every pixel is rendered, only 15% of it is rendered. Everything else is AI-based rendering. So it understands the relationships inside a picture. And it can do that. The same way, even for voice, it goes through patterns. So that part we're doing. But what are we doing to make power consumption for telecom go low? That part I will ask. So that would be a good thing for utilities. I think I can get back to you on it if you can drop me. Sure. As next speaker. Oh, all right. Thank you so much. Yes. Let me get it. Oh. Yes.
Post.
Oh, sure.
Lily? Done? It's done. Okay. So, good afternoon, everybody. As you know, we are here for the AI for Weather and Climate Intelligence session. And soon we will be beginning with that. I request you all to kindly be seated. All right, so I guess we are good to go. So the keynote speaker for this session, we have Dr. Karthik Kashinath. A brief introduction about him. Karthik is a cross-disciplinary leader in NVIDIA's Earth 2 initiative, focusing on large-scale generative AI and HPC technologies for weather and climate science applications. He works across strategy, research, full-stack engineering, product development, and product deployment. Prior to joining NVIDIA, he worked as a scientist at Lawrence Berkeley Institute, National Lab in Berkeley, California, where he focused on earth sciences and computing sciences, specializing in physics-informed machine learning for complex systems. He is trained as an engineer with a bachelor's from Indian Institute of Technology, Madras, master's from Stanford University, and PhD from the University of Cambridge, UK. Please welcome Dr. Karthik Kashinath for his session. Thank you.
Thank you all for being here. It's a great pleasure to be presenting as soon as I can get my slides on the screen. So just a moment. Okay, perfect. Thank you. Okay. Great. Okay. Well, we've got about 45 minutes and plenty of content here, so I'll dive right in. I'm going to present on ways in which NVIDIA is working to contribute towards building AI for weather and climate applications. Thanks for the introduction. And I'm representing a large team of scientists, engineers, product developers, solution architects, and many others. This is called the Earth 2 initiative, so I'll tell you a little bit about it. So first, just the agenda for the next 45 minutes or so, a few minutes on Earth2 and what it's about, what the inspirations are for this work. And then I'll dive right into what we're doing in AI for weather and how we're taking that into operations in collaboration with many governments and institutions across the globe. Then I'll dive into generative AI techniques to emulate ultra-high resolution data sets, like kilometer scale data sets in weather and climate, and talk a little bit about the climate foundation model that we're building called Climate in a Bottle, and then finally conclude with a little bit about our product tech stack. Okay, so this is sort of the story for Earth2. Imagine you could select any region of the planet, and as you can see there on the screen, you might draw a box around India, and then you might ask, what if I want to zoom in further, say into the north of India, or even further into a particular state, or maybe all the way down to the city of New Delhi, and then ask questions about the impacts of weather and climate on food, health, infrastructure, energy systems, and so on. That is sort of the vision for Earth2. The idea is this highly interactive weather and climate information system that anyone can access anywhere on the planet and be able to use it for serving society and planning and various other applications that are impacted by weather and climate. So this is, of course, not entirely a new idea. It's been around for a few years. It's the concept of digital twins. And in particular, our project Earth2 draws the inspiration from the Destination Earth project, which is shown here on the left. Is this sort of image of a globe that's essentially a digital twin of planet Earth. And on the right is these what-if questions that can be asked about various different types of things, including, like I said, energy impacts, utilities, agriculture, etc. This is from a Nature article in 2021, and the Destination Earth project is one of the largest projects in this space and is entirely funded by the European Commission. So you might ask why we care about this problem and what's so challenging about it. So let me just show you what a simulation at ultra-high fidelity of the Earth looks like. This is a model called ICON, which is a Max Planck Institute model that runs at sub-kilometer scales today. And what you're seeing there is the exquisite detail across the planet in terms of both the atmospheric dynamics and also the ocean dynamics and everything else that interacts with the climate. For those of you that are not aware, some of you I'm sure are well familiar with the simulations of these systems. But if you're not aware, on the left is a plot that shows you the scales, both in space and time, for Earth's weather and climate. And you can see there's dynamics happening at very fine resolutions, like microscale, the formation of droplets, raindrops, etc., all the way up to planetary scale. So things like the El Nino oscillations happen at 1,000+ kilometers. So we're talking about a system that spans over 10 orders of magnitude in space and time. And trying to simulate that on a computer requires very high resolutions to be able to resolve all of that exquisite detail. And on the right is a plot that shows you what the compute requirements are for running these simulations, starting at where we are today with the IPCC's CMIP6 data, which is the International Intergovernmental Panel on Climate Change's sort of flagship data set that's used across weather and climate applications. That runs in 25-kilometer resolutions across the globe, so pretty coarse resolution. And that if we take that as the baseline for compute, then scaling up to 1 kilometer requires 30,000 times more compute, and scaling up to 100 meters or finer, which is the scales that you would need to be able to resolve things in cities and so on, requires 500 million times more compute. So this is a computational grand challenge. Now let's add a few more things to the mix there. On the top right is this sort of cartoon from ECMWF that shows that you can't just simulate the system once because we're talking about chaos. I'm sure you've heard about the butterfly effect. So we're talking about systems here that have very wide-ranging outcomes for the same sorts of starting points. So you need to run the simulation many, many times to be able to get a distribution of possible outcomes. And then on the bottom is this new challenge that's emerging now that we can actually simulate these systems at kilometer scale, which is that these models produce petabytes of data per simulation, and specifically for long simulations that are out to 100 years or so for climate systems, we're talking about an exabyte of data. So that's 1,000 petabytes. And by the way, a petabyte is 1,000 terabytes. So we're talking about 1,000,000 terabytes of data that needs to be processed. As you can imagine, that's an extremely challenging problem to work with. So this is sort of the foundations of why NVIDIA is in this. First of all, of course, to be able to serve society and governments and various applications, but also because we have the technologies and the tools to be able to do this at scale. I'm sure you're well familiar with the GPU and also our work in AI and visualization, and those are the three pillars of Earth-2. So just to mention briefly before I dive into the AI aspects, this is some of the work that's been done in high-performance computing, and the leading conference for that is the Supercomputing Conference, where the Gordon Bell Prize, which is sort of the highest award given for computing, was given in SC25 just a few months ago to a NVIDIA Grace Hopper accelerated simulation of the Earth system at exquisite scales, sub-kilometer scales. And this was done on the two machines in the bottom. The first is the Alps machine in Switzerland, and the second is the Jupiter machine, which I believe is in Italy. And these were at 24,000 Grace Hopper nodes. 24,000 Grace Hopper GPUs, 6,000 nodes. And so that's the types of scales at which the HPC simulations run. But as you can imagine, that is very expensive and also takes very long to be able to do these simulations. So that's sort of setting the stage for why AI is necessary and important and actually quite powerful for this space. But before we get into that, let me just call out a few data sets that have been generated from these very large kilometer scale simulations that are actually contributing directly to the AI training that we're doing both inside the company and outside in collaboration with various partners. The first on the left is the 5-kilometer data sets generated by the Max Planck Institute running the ICON simulations, the one that we just saw at the start. And that's about a petabyte of data for 5 years of climate simulations. And we've trained our foundation model on that data. In the middle is data from the Weather Company, which is a private company that works in the weather space across the planet. And they've generated, using MPAS simulations on GPUs, 5 years of data of many different extreme weather events over the last 20 years, and that's about 3 petabytes. And the same by MITRE, which is a corporation that works with the US government, running 3-kilometer simulations of WRF, a model called AceCast, which also runs on GPUs, and 3 years of data. That 1-kilometer resolution is about 8 petabytes. So we've got over 10 petabytes of data that we're training these models with. The second thing I'll mention here is the visualization work that we're doing. And let me just quickly play this video.
Accurately visualizing current weather conditions in high resolution and at a global scale is incredibly helpful to climate scientists. Using NVIDIA Omniverse Cloud, we can look at an ICON simulation of any part of the world at a resolution of 1.25 kilometer. Here, you can see the detail in the clouds over Taiwan, or thunderstorms over Africa that form as the sun rises and its light strikes the clouds in that area. Typical simulations today are done at 25-kilometer resolution and simply can't show these details. Observing the climate in high resolution at a global scale is a powerful tool, but it's also important to be able to show the impacts to specific regions, or even to specific areas of a city. Here's a simulation of Ernst Reuter Platz in Berlin, where we can see how the size and location of buildings impact airflows, based on data from PALM and volumetric data from ICON. This simulation power gives architects and city planners insights into how they can design and build smarter, more sustainable cities, while letting climate scientists gain a deeper understanding of our changing world.
So all of that was done using NVIDIA Omniverse, which is our digital twinning and visualization platform. And we're using that heavily in Earth-2 as well to be able to create these digital twins, interact with them, and so on. We'll come back to a few more ways in which how the AI models that are built by Earth-2 are also connected through Omniverse to be able to use by various users. So here's a snapshot of the sort of timeline of Earth-2 since its inception in November 2021 by our CEO, Jensen Huang, at the GTC conference. That was sort of obviously the most important point that was made about NVIDIA's involvement in this space. And then since then, we've been building up towards various different applications. Without getting into every single blob here, I'll just point out that the ones in gray are important events that either our CEO or other executives from NVIDIA have participated in, contributing to the conversation and the technology development in this space. And then in green are all the different models that NVIDIA Earth-2 has built over the last 4 years. And as you can see, zooming all the way to the right end, just last month we released 4 models for different time scales and different spatial scales, both global as well as regional, and also for data assimilation, which is a very important step in weather and climate prediction. So let me skip over to some more context for Earth-2. It's a program that is funded and developed by NVIDIA, but is in collaboration with international weather and climate science and technology. We think that our AI and full stack engineering expertise complements the deep research capacity and knowledge that exists in academia and government, and we wouldn't be able to do this work without that collaboration. So on the left are a few logos of the different organizations that we worked with, including, I'll mention a little later about the work that has been done with the Ministry of Earth Sciences and the IMD department. As you can see, there's various other institutes across the planet, including in Asia and Europe and North and South America as well. On the right are the private companies that we work with in this space, and you might recognize some of the names there. Across the board, we're doing things, everything from data to AI models to deployment on various different applications, insurance, reinsurance, lots of other applications of course, weather and climate intelligence. Okay, so we're about 12 minutes in, and that's the sort of context setting for what Earth-2 is and what we do. Now I'll dive right into the sort of core of this talk, which is about AI applications in weather and climate. And I'm going to pivot from just describing innovations that are happening in research and technology all the way into operations as well. So again, some of you are in this space and you're probably well familiar of the way in which AI has exploded in this space, but if you're not, this is sort of a single snapshot that shows the evolution of AI in weather and climate applications in basically about 3.5 years' time, which is pretty incredible given that this stuff did not exist in 2020 in this space. And today we have papers, lots of papers in Nature and Science on AI-powered forecasting for weather and climate. But perhaps more importantly, the first operational AI model was launched by ECMWF, which is the leading organization, the European Center for Medium Range Forecasting. And this is being used right now, real time, for operational weather forecasting, AI-based. On the bottom right is a conference that I was invited to present at the WMO, the World Meteorological Organization of the United Nations, where there were 180 countries that were participating in this, and there were at least a dozen countries that are already thinking about deploying AI in operations, and several of them that are actively working towards getting there. So this is no longer a research or development phase. This is very much an operational task. So before I get into some more detail on the climate, I'll talk a little bit about AI for weather. And as I mentioned, we have about 12 models right now that we've developed, and I can't possibly cover in any depth all 12 models in 45 minutes. And so I'll just mention briefly a couple of models, pointing out the kinds of things that you can expect for developing AI tools and technologies for weather and climate. Our flagship model is the ForecastNet model, and it is here on the left. It uses a combination of neural operators and transformer blocks, and this is all in the paper at the bottom. You can go check it out on arXiv. It's got obviously all the details about how exactly this model is built and trained. But just to point out a few key things about why AI is such an attractive thing in this space. Firstly, it trains in about 1,000 GPU hours, which for those of you that work in computing is not actually a very heavy compute capacity. It's accessible even on relatively small clusters to be able to train these models. But more importantly, in inference, these models are 1,000 to 10,000 times faster than anything else that's used in the space, numerical models or other types of statistical techniques. So there's a humongous speed and therefore power savings as well that comes along with the use of AI. Obviously, the thing that's worth noting is that you train once and you can inference many, many times. You might need to retrain once you've got some new data sets, but you could potentially fine-tune once you've already trained a model. So that's the upshot for why these models are being adopted so quickly in this space. But let me get to what the speed actually enables, besides just delivering the results 1,000 times faster. Recall that these are chaotic systems, and so we need to run many, many simulations of the same system to be able to characterize the probabilities of a heat wave 2 weeks from now, or what climate impacts might look like a year, 5 years, 10 years ahead into the future. And this sort of cartoon on the left shows many different simulations of the most extreme heat wave in Africa, which crossed, I think, 56 degrees Celsius in North Africa. And this shows that using AI, you can run these systems so much faster that you can now generate a 1,000-member ensemble of different types of extreme events. On the right is showing also what that ensemble brings you, which is the estimation of the probabilities of the risk of these events at very, very low probability events that have very high impact. So as you can see there on the right is blue curves that characterize increasing probabilities, highest at the center and lowest at the far ends. And most extremes lie at the far ends of these probabilities, meaning that you need to be able to simulate many, many times to capture those extremely low likelihood, high impact events. And here we're showing, using the ECMWF ensemble, IFS, the red triangles show that you can capture some of those probabilities, but not quite the tail events. And using an AI ensemble, a forecast.net, the model that we developed a few years ago, those are the blue dots, and you can see that when you run a 1,000-member ensemble, you can flesh out the very low likelihood events much more accurately using these models. So let me demonstrate what that looks like for hurricanes in the Atlantic, if this plays. So what we're seeing here is a real-time AI ensemble that's generated using forecast.net. And you can see you can generate as many trajectories as you like, in this case 1,000 trajectories of possible ways in which a hurricane might evolve and impact different parts of the United States. You could do the same thing for heat waves in India or for other types of extremes in other parts of the world. And I'll come back to that in a later part. So I'll mention a couple of use cases and applications, and maybe I probably need to accelerate a little bit given that I've got quite a lot more content to get through. So the work that's being done here is in collaboration with AXA, which is in the financial services industry. And we're using forecast.net to simulate hypothetical scenarios and outcomes many, many times and ask questions like how much more frequent are these extreme events going to be because of climate change? How much more severe can they become? What's the estimated risk? How is it different from the past? And so on. And that's, of course, being used for disaster preparedness and emergency management. This is a particular storm that had an extremely large impact in Europe a few years ago, I believe 2024. And the economic damage from this one single storm was 30 billion euros, which is obviously a very high price to pay, besides 180 deaths across the region. And it's only expected to get worse with climate change. And so estimating these types of tail events is very important for planning purposes for emergency response and disaster preparedness as well. And getting into a little more detail on this, we ran this model, forecast.net, out to much longer timescales to be able to simulate what the possible outcomes might be over an entire season. And this was done in collaboration with JBA, which is a risk management company based out of London. And they were able to show that the model was able to simulate quite accurately using historical events, the probabilities of occurrence of these events, and that gave them the confidence to be able to use this for future estimation of risk as well. As you can imagine, it's not just about running an AI weather model to be able to advise, say, a water manager or a city planner. You need to then connect that to diagnostic models that takes it all the way down to impacts. And so that was done, again, in collaboration with JBA, and they were able to develop these add-on models on top, which actually they've been doing for quite a long time already, which is to estimate what the rainfall runoff would be and how that would actually result in flooding in different parts of the region at a pretty high resolution as well. And so you can see now using AI, you can simulate these trajectories much, much more quickly, and therefore you not only get an end result much faster, but you also get better probabilities. So how are we leveraging this for getting into climate timescales, which is, of course, much longer than weather timescales? One way is to actually extend these out, and so you can actually run these simulations that are developed for weather forecasting out to much longer timescales, and we're doing that right now for subseasonal to seasonal timescales, and also all the way out to climate timescales, decadal timescales. And we're asking things like, would we have rain, say, 2 weeks from now, during Holi, or could we ask what the likelihood of drought is in North India next year, for example, or 10 years from now? As you can imagine, when you get to longer timescales, it's not just the atmosphere that's important. You need to couple that with the ocean, with the land surface, and so on, especially to be able to capture things like the El Nino oscillations, which are driven quite heavily by influence from the ocean. And this is an example of how this coupling can be done. So we're using our AI atmospheric model and coupling that with an AI ocean model, just like you would do for a numerical simulation. And we're running that out now to much longer timescales and being able to predict the ocean states as well as the atmospheric states into the future. This is just showing how these models are being validated across the historical data sets that we have, both observational as well as reanalysis data sets. And you can see here, without getting into too much detail, the red lines are the deterministic forecasts from the AI model, and the ensemble mean is the dark red line, which probably doesn't show up that clearly on the screen. But you can see that the red lines are hugging the black observational line, which is showing that across 5 years of different types of events, the AI model is able to capture quite accurately the evolution of the El Nino over those 5 years. So there's many more applications that ForecastNet has been used for in collaboration with various other partners. This is just capturing on a single slide the different ways in which this model is being used by different organizations across the globe. And I'll get to a couple of more applications in just a moment, but this gives you a sense of how the models are being adopted in the industry and in government and academia. So this is work done by the Indian government, and I think it's one of the most impressive applications of AI in operations in this space. And credits goes to the Indian Ministry of Agriculture and Farmers Welfare that led this project in collaboration with many others, including some of the developers of ForecastNet. And I'll just mention briefly what the work here was, and it was partly done by the University of Chicago's human-centered weather forecasts, at least on the AI side, and then, of course, deployed into operations by the government. And what they did was they brought together a team of climate scientists, AI experts, economists, and social scientists to be able to benchmark and generate these forecasts and then work with the government in order to help them be able to disseminate that out to the public. And the impact was that 38 million farmers were issued information about not just the weather in the next 2 weeks, but also over the entire season as to when the onset of the monsoon was going to be, if there were going to be any delays in the onset, and as the monsoon progressed into the country, whether there was going to be stalled phases when there might not be any rain, or there might be too much rain in some regions, etc. So there was quite a lot of information that was produced by this work, and it made a remarkable impact on the agricultural industry in India just in 2025. So this is a very fresh example of applications of this in operations. And there were messages being sent out to farmers. I think 38 million farmers were receiving these messages, things like what's shown on the top right, on their phones, basically. So this is very rapid dissemination of this work. Without getting into too much more detail, this is to make the point that there's great leadership right here where we're standing and sitting for this kind of work in this space. And I think it's a very exciting time. And I expect to see many more of these types of initiatives across various other industries being taken both within India but also outside the country. And in fact, this is a great example of how India is showing leadership in this space of AI-based weather and climate prediction. So with that, I'll get to maybe a little more of the mechanics of how this sort of thing works. And this is just to give the University of Chicago example. And of course, it's a much larger team than that. This is the type of collaboration that's needed at least at the research and academic level to be able to then connect with the operational people in governments across the world. This is some of the folks that were involved in this work. The AI and weather experts were Pedram Hassanzadeh and his team, and they're our collaborators, and we developed the ForecastNet model with them first in 2022. Then, of course, there were other teams, including the Nobel Prize-winning Michael Kremer economist, who also is at the University of Chicago and worked on the economic side of things. There were teams working on the physics of monsoons from UC Berkeley, Bill Blues, and others, and also teams working on the agricultural needs. So all of that worked in sync together with the operational folks here based in India to be able to create this kind of impact. Okay, so with that, I'll pivot to some more specific details on how we're getting down to ultra-high resolutions and how this is being used for various applications. Recall that we need to get to very high resolution in order to be able to predict what's going to happen on the ground, what's going to impact farmers or transportation systems or energy systems and so on. So this is perhaps a video that's familiar to you. This was released by OpenAI. This is the first version of their Sora video generative model. And this entire video was generated by AI using a single prompt, and that prompt is shown in the bottom. So a user basically keys into something like ChatGPT, in this case Sora, generate a photorealistic video of two pirate ships and a coffee cup, which is obviously quite ridiculous, but look at what is produced by the AI. If anyone in the room is familiar with computational fluid dynamics and simulating these systems, there is very realistic detail in the flow of the coffee here, and I think I'm drawn to that as a fluid dynamicist myself. But also that these video generative models have extremely high fidelity in generating physical science data. And so we're asking the question, can we use the same types of models that are used in computer vision, such as OpenAI's Sora, which are diffusion models, to be able to generate high-resolution details of Earth's weather and climate? So our first model in this space was a model called CoreDiff, which is a generative diffusion modeling framework for kilometer scale downscaling. This is showing you what the model does. You take a low resolution data set from, say, the IPCC CMIP6 or from other archives, and then you pass it through the model and you generate kilometer scale detail. And that's 16x in each dimension, so it's 256 times higher resolution than the native data set that was ingested. And using that sort of resolution, you can then see the specific details of things like tropical cyclones or other types of extremes which have a very high fine resolution detail. And this was published in Nature last year. And this is an example of the work that the Taiwanese Weather Bureau has been doing using this model. And this shows how they're deploying it in operations for typhoons impacting Taiwan. And you can see there on the outside is the low resolution data. The box is where the generative AI is producing the super resolution outputs using CoreDiff. And as you can see there's far more detail inside the box than outside the box, which is really important for disaster management and emergency preparedness. Okay, so that's obviously a pretty small scale. Taiwan is a fairly small country. It's shown on the bottom right. That's the scale of Taiwan. India is about 100 times that size, and the United States is 300 times the size of Taiwan. So you might ask the question, how can you deploy these models at scale much larger than the ones that they've been developed at? And the very exciting thing is that these diffusion techniques can be scaled out to very large domains using patch-based approaches. And I won't get into the specific details of the approach, but you can go check it out in the paper and also on the links on the bottom. But essentially, you can you can tile the entire planet using many different tiles that are all doing the same thing in terms of the mechanics of what the super resolution model is doing, and put together with appropriate boundary conditions, you can generate the kind of detail that you see here. So I'm very thrilled to announce that CorDiff has been deployed at these continental scales and is being used in operations for various different applications. For example, the weather company, which I mentioned earlier on, one of the largest companies in the weather business, and they help guide decisions that are driven by weather and derive a lot of skill, but also impacts on various different types of metrics. They are using the same model, CorDiff, to do super resolution of very different complex fields like wind fields, precipitation, and types of precipitation across the United States. And with that, I'll pivot to some of the work that we've been doing in the climate space, so moving towards foundation modeling, which I'm sure you've all heard of and is one of the most exciting directions in AI for science today, which is how to build these climate foundation models. Just to recap, a few desirable properties of a foundation model are, first of all, it needs to be useful across a wide variety of tasks. So it needs to have sort of foundational capabilities. It needs to bridge very different data modalities. So you could combine things like text, audio, image, many different types of scientific data sets across different resolutions, et cetera. Have diverse functionality, and importantly, to be able to enable users to do things with it, it needs to be interactive, so a system that you can actually get a response from on very short timescales, like we do today with ChatGPT or other types of LLMs, and also to be able to scale it out to very high resolutions and global scales. And as I mentioned at the start, we're talking about simulations that can produce 1,000 petabytes of data today, and being able to parse through all of that data is essentially impossible, no matter how large your computing system might be. And so we want to be able to distill the information that is contained in those 1,000 petabytes into a foundation model that can then be queried by users on many different types of applications. So this is one example of the kind of querying that you might do with the climate foundation model. You could condition the model on climate controls, things like El Nino, the Indian Ocean oscillations, other types of controls of the climate in this region, and then ask questions like, what is the potential for a delayed onset of the monsoon next season, and then be able to generate many different types of scenarios of that out into the future. So you could ask that question for, say, for example, 2026, and whether the monsoon that typically arrives in early June is going to be delayed or is going to arrive earlier, and so on. So, of course, that's the dream, and that's things that we're working towards, but I'll show you what we actually have currently working. Without getting into too much detail, because I want to make sure I have enough time for questions, the data sets that we trained Climate in a Bottle on are right now just two, but we're expanding this out to many more data sets. One was icon simulations at kilometer scale, the ones that we saw earlier in the talk. And the second was the ERA5 reanalysis dataset, which is sort of the gold standard for the observed history from 1950 to today. And that's published by ECMWF, and the link is shown there in the bottom. So both of those datasets were ingested into the training of Climate in a Bottle. And then in inference mode, this model can be run using a pretty simple set of user-defined inputs like the day of the year, the time of the day, the sea surface conditions, and a couple of more steering fields. And then because this is a diffusion model, it takes in white noise, and then it generates high-fidelity outputs, both at coarse resolutions like 100 kilometers, but also at very fine resolutions, 5 kilometers, using the batch-based super-resolution model CorDiff that I talked about, which has been scaled out to the entire planet. So what are the types of tasks that you can do using this model? First is you can ask these what-if scenarios, like the one that I described about the onset of the monsoon. But importantly, you can also fill in channels. There's lots of missing data in these weather and climate data sets because of various reasons, and you could use these different data sets to infill the missing data that exists in these data sets. The third, of course, is downscaling, which is to increase the resolution of the data, potentially to kilometer scale and finer. The fourth is multimodal learning, so learning from many different modalities, including potentially text and speech and so on. Correcting biases in data sets, so correcting different types of biases in different models, which of course we all know is an issue with many of these climate models. And then finally, to emulate the dynamics of the climate system itself. The paper is shown in the bottom. It's an archive and it's under review right now with Nature. And the code is also on GitHub and open source and publicly available. So this is just a couple of slides showing the applications of climate in a bottle to downscaling. For example, here on the top left is a coarse resolution data set over the United States. It's actually a global data set. This is an image just showing the US at coarse resolution, and then the output is the kilometer scale detail produced by climate in a bottle. Now, the very interesting thing is that you can use the same input and specify the flavor of the model that you want the output to resemble. So, for example, you could train on 2 different kilometer scale data sets like ICON and WRF and ask the model to produce high resolution details that are consistent with each of those training data sets using essentially just labels. You can also infill, like I said, between different data sets depending on where there's missing data. This is an example of infilling and also bias correction, both in a single shot. So we're correcting the errors in a particular field of the ERF5 data set in radiation, and also infilling high resolution detail using icons. So that's an example of a combined task of infilling plus bias correction. And then this is another example of debiasing or bias correcting many different types of fields in ERA5. So the next aspect that I'll mention here is of course the computing performance of these models. And of course, the first time you train a model, it's likely going to be quite expensive and slow to train. But then you can optimize the performance of both the training and the inference on our GPUs. And this is showing the kinds of accelerations that have come through those performance optimizations, which recall are quite critical for developing a system that's interactive, so where users can put in a request and get a response in less than a second or so. And this shows that we're now pretty close to essentially the theoretical maximum, not quite there, of course, but getting quite close to it. And that's enabled the interactivity that you see here.
NVIDIA's Climate in a Bottle was demonstrated at the recent GTC DC and supercomputing conferences, where users could explore interactive what-if scenarios for extreme weather risks. Conditional extreme weather generation transforms traditional modeling from hours to seconds, enabling rapid counterfactual analysis. You can generate targeted extreme scenarios on demand without mining through massive data sets for those rare events. NVIDIA's Climate in a Bottle was demonstrated at the recent
I don't know why it's playing the same audio again, but this is the most recent work that is actually hot off the press, just happened a couple of weeks ago. And here we're using the same thing for, if I can get it to work, simulating tropical cyclones in this region in the Bay of Bengal. And this is associated with, of course, the monsoon season, but also with other types of impacts in the November to December timeframe on the East Coast. And here we're using the same Climate in a Bottle foundation model to be able to generate on-demand tropical cyclones in this region. Remember that I mentioned the user specifies the time of the day, the time of the year, and sea surface conditions. And then the model spits out these ultra-high resolution tropical cyclones. And so we've done this for other regions around India as well, in the Arabian Sea and the Indian Ocean. And so right now we actually have functionalities that are, of course, to be tested in terms of its reliability and accuracy in this region, but at least it's certainly a proof of concept that is working. Okay, so in the next few minutes, I just want to describe the types of tools and technologies that we're putting out, and most of it is open source, and I would highly encourage you to check it out and develop on top of the stuff that's already out there. So the first is to to remember what's driving the adoption of AI in this space so quickly. Firstly, a lot of the open source work that's out there is of very high quality and it can be built on top of, and that's one of the things that's accelerating the adoption. The second is these models are relatively easy to train. Like I mentioned, it's about 1,000 GPU hours for some of the models that we train. And that's compute that's readily available at institutions across the country. I'm sure all the IITs have clusters that can run these models. But importantly, the speed of inference is 10,000 times faster than numerical models, and that means you can do a lot more with these models. They're also much more compute and energy efficient. And the other is the usability. So these are models that can be optimized for specific tasks. You can fine-tune it for different types of applications and build entire end-to-end workflows. What we expect some of the future drivers to enable further adoption of this is the high-frequency on-demand output generation. For example, you might ask in your specific region what the impacts of weather are going to look like at any time a new observational data stream comes in. We expect the accuracy and skill of these models to get better. It's already better than some of the numerical models in the weather forecasting space, and I only expect that to get better with time. And then, of course, multimodal foundational models, such as OpenAI Sora, are types of things that one could imagine developing for AI in weather and climate applications as well. And that's, as I mentioned, the sort of inspiration and goal for Earth-2 as well. And then fine-tuning these models to many, many different types of customized tasks and reducing the barriers to operationalization are likely going to drive the adoption of this further. So our tech stack for NVIDIA Earth-2 is shown here. This is, of course, just a cartoon, but I'll show you the links in a moment. There's a stack for simulations, so high-performance computing and GPU-accelerated simulations of various different weather and climate codes. And then we have a framework for AI training for different types of AI models, training them from scratch or using pre-trained models and adapting them. And then we've got a library of AI models that are already trained that can be inferenced, and the optimized inference is accessible through also an open source software that I'll just come to in a moment. And then finally, visualizing this using something called Omniverse, which you probably heard about, which is the visualizations that I just showed earlier on. So the training stack is Physics Nemo, or I guess the training framework is Physics Nemo, and this is shown here. Again, the types of things that you can do with it are, first of all, it's open source, so it's publicly available, and the link is down there at the bottom, the GitHub link. You can build on top of it. It's built on PyTorch, and it's got lots of optimized libraries that one can use. It's got most of the state-of-the-art architectures in this space for weather and climate, and it's also got lots of recipes that one can use to customize it for different applications. It's highly optimized and scalable on our hardware and has multimodal capabilities and optimized ETL, extra transformer load. It's also optimized and scalable for larger systems like multi-node distributed training if you'd like to train big models as well. And then finally, fine-tuning it and extending it is also quite straightforward. The second is the inference platform. That's called Earth-2 Studio. There's a bunch of production-ready AI models that are already out there, 50 plus if I recall right. And these are some of the models that we've developed internally in Earth-2 that are also available in Earth-2 Studio. They're also hosted on Hugging Face, which I'm sure you've heard about, for inferencing many different types of AI models. This is a list of the types of models that exist in Earth-2 Studio as of, I believe, a few months ago. And you can see there's quite a long list, including many of the open source models developed in the field, ECMWF, CIFS, Microsoft's Aurora, and so on. And then using the inference scripts and recipes that we have there, you can build on top of that and use it to essentially deploy a model with basically a few lines of code. So it's quite accessible. And I will then wrap up with this description of, let's see. I think I might have lost Wi-Fi, so I need to reconnect. Oh. Okay. I don't know why it keeps toggling back and forth, but hopefully. Yes.
Weather has a profound impact on our daily lives. Predicting how it will affect agriculture, energy, aviation, and emergency response is critical. But the atmosphere is chaotic, and forecasting is complex. NVIDIA Earth 2 changes the paradigm. It accelerates the AI revolution in forecasting by offering developers and researchers an open set of tools that lowers the barrier to AI-enabled weather simulation. Building on the impact of models like ForecastNet and CoreDiff, NVIDIA Earth 2 is now a complete portfolio of open models. Introducing Earth 2 Global Data Assimilation, Nowcasting, and Medium Range. To initialize predictions, Earth 2 Global Data Assimilation models turn observations from diverse sources, like balloons, satellites, and stations, into atmospheric states in seconds, a task that previously took hours on high-performance computing clusters. Earth 2 nowcasting models offer severe weather prediction at continental scale from 0 to 6 hours. They represent the first time AI has surpassed the accuracy of physics-based forecasting of storm evolution. Earth 2 medium-range models deliver 15-day global forecasts with accuracy that outperforms other open models on standard benchmarks across more than 70 variables. Earth 2's models span the complete forecasting pipeline. When they're combined, weather can be simulated at speeds previously impossible, minutes instead of hours or days. And because Earth 2 is completely open, not just model weights, but inference tools and training frameworks too, developers can customize and fine-tune simulations to specific needs, using their own data and infrastructure to build sovereign weather and climate predictions with full control. See into the future of weather with NVIDIA Earth 2.
Okay, thank you very much for your attention, and I'm happy to take questions. Yeah.
So how close are these open source weather forecasting models compared to when we, let's say, compare it with something which is commercial, let's say DNV, GIS or of the world, where there are more license? Or in other words, what is the make for, let's say, a short-term weather forecasting, let's say for 14 days? What could be the range of the MAPE or RMS?
Can you explain what you mean by MAPE?
Mean absolute percentage error.
Ah, okay. Yeah, the RMSE, yeah. So the open models in the medium range timescale are already surpassing numerical models. So the ones like ECMWF's IFS is the gold standard for numerical prediction at that timescale. The ones at much higher resolutions and shorter timescales like nowcasting, so predicting like the next 6 to 12 hours, they're not quite as good as the numerical models just yet, but they're about 6 hours on average. I'm sorry, 6 minutes or so behind in terms of their forecasting horizon. The data assimilation models are also not quite as good as the numerical models, but they're getting there. And I would say AI data assimilation is going to be quite big in the next couple of years.
Karthik, I want to ask one question on this power sector. We are facing quite a lot of issue in renewable energy forecasting. Many DREs are coming into place, distributed renewable energy. We have 30 gigs of rooftop solar installed in the span of 2 years.
Okay.
So as in India, we are actually facing in RE forecasting as well, and that's the reason we are not able to manage our grid operations. So what is happening in the RE forecasting domain is right now we are dependent on I&D sources, India Meteorological Department, and that is providing at a cost of 12 kilometer into 12 kilometer. And then we are getting it at an interval twice in a day, they are giving twice a day.
Okay.
but we need kind of, in India, the power sector is transacting at a 15-minute blocks and regular updates are happening.
Yeah.
So what do you think means, as we are increasing our RE, what should be our pathway, and how we can solve this problem?
Yeah, it's a great question, and that's exactly the type of application that CoreDiff, the model that I showed, the super resolution model, you can take the 12 kilometer data that you have, and if you've got training data to get to even higher resolutions than that, both in space as well as time, you can then feed in your IMD data and then generate much higher frequency outputs and also much higher resolution in space, which I think would be quite useful for your specific application.
And how it is happening in the West is, means their renewable energy sources are increasing quite a lot. So at what resolution they are getting into it? Since we have demanded to IMD for 4 kilometer into 4 kilometer from CES, Central Electricity Authority. But I think
I think you can go finer than 4 kilometers, yeah. Because if your input is at 12 kilometers and these models can do 16x super resolution, then you can get to sub-kilometer, 800 meter scale.
I have a question here. We talk about the nowcast and medium range. So do we have something long run also? Because I'm like working very closely with CA on developing a long-term tool for the country in terms of demand forecasting, and the challenge we face is again with the IMD data.
Yes.
You don't have the long-run forecast. So so these are like, we generally do the past simulations from the past data, and then we do the forecasting. So and of that you have a lot of errors, and even in the short run, what we find is this, that the forecast, our forecasts go haywire because of the weather. So, weather is a very critical input for demand forecasting, both short run and long run. I'm just like adding a point, like what he was saying. In the power sector, it is very crucial. So, would want to hear from you, like, the short run, long run, what kind of products we can use.
If I can bring back the slide that I showed in my talk that has the full set of models that we host. I can also give you the link to the specific page where you can. There you go. Okay. So this shows in green are all the different models, and I only talked in detail about ForecastNet, which was our first sort of flagship model in the medium range timescale, and also about CoreDiff, which is the super resolution model. But you can see here that we have models for sub-seasonal to seasonal forecasting, which is the one up there, DeLeSim, which is deep learning Earth system emulation. That's for the 4 to 10 week timescale. And then, of course, the climate model that I talked about, Climate in a Bottle, that's for much longer timescales as well. And then we have Stormcast, which is the regional model for the nowcasting applications in the 0 to 12 hour timescale. And then on the bottom, Region and HEAL-DA are data assimilation models. Region is for regional data assimilation, and then the HEAL-DA model is for global data assimilation. Yes?
Since you are running so many models, are you planning, is NVIDIA planning to give open source, like make their data open source so that
It's already open source.
Okay, so
Yeah.
for CoreDiff is the data available so
Yes,
that
it is,
anybody
yeah.
can just
Let me-
download the data and use it?
Yeah, let me show you the link to that if you have it.
There's so many models, like which one to use, like,
Well, it depends on the.
asked us, like, you have so many of these, which one we should use?
It depends on the time scale. So for the application that he talked about for renewable energy forecasting at very high resolution and short time scales, you would use Stormcast because that's the model for 0 to 12 hours. But if you're talking about planning for agriculture this year, post-monsoon, then you want something that's 6 months or further beyond. And so you would use DeLeSim, which is for sub-seasonal to seasonal timescales. And then, of course, if you're building a new city and you want to plan for energy or water for that city 10 years out, then you would use Climate in a Bottle, which is a climate timescale model. I know that can be a lot of information to digest in a few minutes, but if you go to the...
Do we have a glossary of it, means which of the model would be suiting for?
Yeah, let me just show you the link so you can actually pull it up on your phone and see what's available. So I think your question was about CoreDiff, so that's one of the links if you want to take a photo of that. But let me get to the main page that has... So this is for training. So if you want to train your own models, you would go to Physics Nemo. But most likely you can use the pre-trained models for the different applications that you want to maybe test out first. And that's available both on Earth-2 Studio. So if you just Google search Earth-2 Studio, you'll get the GitHub link to that. And then on the right is the Hugging Face link that has all the pre-trained models. So you can access it there. And this is the list of models on Earth-2 Studio. And like I said, there's over 50 models out there, including ones that have been developed by the community. So like ECMWF's AIFS is also in Earth-2 Studio.
Yeah. Excuse- Just one more question.
There you go.
So now that the physics-informed AI models are performing at par with the WRF weather models, so what do you think is the future of these dynamical models like WRF or ICON? Like
That's a great question. Yeah, I mean, it does beg the question, right? What's the future of numerical weather prediction? I think it's still very important because, first of all, many of these AI models are trained on the outputs of numerical models. So if you need to get to even higher resolutions, say to 10-meter scale, imagine you wanted to simulate like the wind in this room. You would still need a numerical model to be able to do that because I don't think there's any pre-trained AI models for that.
But I think the AI models, they can generate their own input data sets, which can be fed back to the network, and then.
Yeah.
But maybe there might be some inconsistencies in them.
Exactly. I think you still need a ground truth besides observations, which of course is the gold standard ground truth. But we don't have observations for everything everywhere. So you would still need to simulate if you want to create training data sets. So I think there is a future for numerical models in that they can be used for generating very high fidelity and very high quality data sets that then AI can be trained on.
Thank you.
Yep.
So in my experience, like we work with IMD and a couple of US institutions. In India specifically, the models that are trained over the global data, since the data quality is much higher over America or Europe, and India has a lot of sparsity of data, how do you deal with the sparsity of data that happens in data poor regions like in the global south, like in India and other regions? Because we struggle a lot with that issue.
Yeah, that's an excellent question. And I'd say that there is companies that are developing observational data streams that can augment the observational data sets that are publicly available or generated by, say, ECMWF or IMD or others. So I think that's one way to increase the density of high-quality data in this region. The other is, of course, to use the numerical simulations that are run by IMD, for example, as training in combination with observational data that might be densely available in other parts of the globe. So the transfer learning that you've seen in some of the work that I showed, you can learn the quality of observational data maybe over Europe or North America, and then transfer learn that to India using the numerical simulation as a basically an additional modality.
Okay. Thank you.
I believe we have space for one last question.
Would you consider Earth-2 as a world model for like Earth's atmosphere? And would you consider Earth-2 as a world model for Earth's atmosphere? If so, I'm curious about something. That world models work the best when you generalize them more than the data. You mentioned that this has been trained on past 50 years of data. So what if you ask something like, if it can simulate a world where it's like 3-degree temperature increase in a year. Now it has not seen that data, and the data that it's trained on in the past 50 years would be comparatively more cold sort of data. So
Yeah, that's a
will
great
it
question.
be able to meaningfully extrapolate, or will it just make guesses after that?
Yeah, so I would say if you use the model that's only trained on the past and ask it to extrapolate out to the end of the century, it's likely going to make up and hallucinate stuff. But the good news is that there are simulated data sets for future climates. Of course, the uncertainties are much larger when you get to the end of the century with a 3-degree warmer planet potentially. But the CMIP6 data set that I mentioned, which is the IPCC's climate model intercomparison project, that has, I think, 50 or so different climate models in there that have all simulated the exact same set of scenarios across many different types of conditions. So it's a pretty rich data set that you can train on and then use that to extrapolate. So
That's it. Thank you.
is that it? Okay, thank you.
So, on behalf of the India AI team, I would like to thank Dr. Karthik for a very enriching session. And so, on behalf of India AI,
Thank you.
great. So, also, dear delegates, kindly note we will conclude all our sessions by 4:30 p.m. today, and you are requested to exit the Bharat Mandapam venue premises by then. You're very well welcome to explore the expo arena that will be open for you till 8 p.m. today. Thank you.